Module 8, Lecture A, DP Fundamentals. By the end of this lecture, you will be able to identify overlapping subproblems and optimal substructure in candidate problems, derive recurrence relations that define dynamic programming solutions, and implement memoized recursive solutions in Python to improve performance over naive recursion. Core DP concepts. Recognizing repeated subproblems. To find repeated subproblems, break a complex problem into smaller tasks and check whether the same tasks appear multiple times in your solution. This often happens in situations like sequences or combinations, where you keep answering the same question with only slight changes. For example, in planning a road trip, you might repeatedly compute the cheapest route between cities. When you notice that a calculation like this recurs, you have identified a repeated subproblem. Recognizing these is essential for dynamic programming because it lets you solve each subproblem once and reuse the result, saving time and effort. To detect repeated subproblems, imagine a simple recursive solution and pay attention to how the recursion tree expands. Look for the same inputs or states causing the function to be called more than once. For example, in a scheduling problem, you might repeatedly evaluate the same combination of remaining time and remaining tasks. When you notice the same state appearing in different branches, you have found overlapping subproblems. The key is to focus on the state itself rather than the specific path taken to reach it, so you can avoid recalculating the same work. In many real-world problems, the same types of decisions must be made over and over, such as planning daily truckloads or repeatedly allocating budgets across investments. These situations involve recurring questions about the best outcome from a given state. By recognizing that these are overlapping subproblems, you can use dynamic programming to solve each distinct case once and store the result. This allows you to reuse previous solutions instead of redoing the same work, leading to a more efficient and structured problem-solving process. Python code. Recognizing repeated subproblems. This example uses the naive recursive version of the Fibonacci function to show how the same subproblems are solved over and over again. By tracing the recursion tree, you can see that identical inputs are recomputed many times. This visual pattern helps you clearly recognize overlapping subproblems, which is a key idea in understanding why naive recursion can be inefficient and why techniques like dynamic programming are useful. The script does not need any pip install commands because it relies only on Python's standard libraries. All the features it uses are already built into Python, so no extra packages are required. This makes the script easier to run, avoids dependency problems, and helps it work consistently on different systems where Python is installed. We begin by importing the functools library, which provides tools for working with functions, including decorators. In this script, functools is used to build a decorator that counts how many times a function is called with particular arguments. This allows us to track repeated subproblems in recursive functions, such as a naive implementation of the Fibonacci sequence. The setup is important for analyzing how often the same inputs are processed during recursion. We define a decorator called countCalls that tracks how many times a function is called with each specific input. Inside the decorator, we create a dictionary that records how often each input value appears. The decorator returns a wrapper function, that, whenever it is called with some value, increases the count for that value in the dictionary, then calls the original function and returns its result. The dictionary is attached to the wrapper so we can later inspect how many times each input was used. Inside the decorator, we use a dictionary called counts to record how many times the function is called with each argument value. Each unique input value serves as a key, and its associated count is updated whenever the function is called with that input. This lets us quickly look up and modify the number of calls for any specific argument. Tracking these frequencies is especially useful in recursive functions like a naive Fibonacci implementation, because it helps reveal repeated subproblems. The code adds extra behavior around an existing function so it can count how many times the function is called with each specific input. It does this by defining a new wrapper function that accepts one argument and performs the counting before or after calling the original function. A utility from the functools library is used so that this wrapper keeps the original function's metadata, such as its name and documentation string. This preserves clarity and consistency when the function is inspected or documented. This line updates how many times a specific input value has been used by the function. It looks up the current count for that value in the dictionary, treating it as 0 if it has not appeared before, then adds 1. In this way, it records how often each input is passed to the function. Tracking these counts helps reveal repeated subproblems by showing which inputs are recalculated multiple times. This line in the decorator calls the original function with the current argument and returns its result. At the same time, it lets the decorator count how many times each specific input is processed. By tracking how often each subproblem is solved, we can see how frequently the same work is repeated. This is key for understanding why the naive recursive Fibonacci approach is inefficient. The code attaches a dictionary called counts to the wrapper function to record how many times each input value is used when the function is called. This lets us track how often each specific argument appears during execution. By storing this information directly on the wrapper, we can later inspect it easily and see how frequently each subproblem is recomputed in the recursive Fibonacci function. This helps analyze the function's behavior and identify repeated work. The code returns a version of the original function that has been wrapped with a counting feature. This enhanced function keeps track of how many times it is called with each specific argument. You can still use it just like the original function, but now it also records how often each input occurs. This is especially useful for studying recursive functions and spotting repeated subproblems in their execution. The Fibonacci function here is implemented using a simple recursive strategy and is wrapped with a call counting tool that records how often each input value appears in the recursion. It uses a base case where inputs of 0 or 1 are returned directly. For all other inputs, it calls itself twice, once with the input decreased by 1 and once with the input decreased by 2. This design clearly exposes overlapping subproblems because the same Fibonacci values are recomputed many times for the same inputs. In this part of the code, we define the base case for a recursive Fibonacci function. When the input value is 0 or 1, the function simply returns that value. This matches the definition of the Fibonacci sequence, where the 0th number is 0 and the first number is 1. This base case also stops the recursion, preventing further calls when these values are reached. This part of the code handles the recursive case for computing Fibonacci numbers by breaking the problem into two smaller calls. It calculates the Fibonacci value of n-1 and adds it to the Fibonacci value of n-2. This illustrates how naive recursion creates overlapping subproblems, because many of the same Fibonacci values are recomputed multiple times. As a result, the approach is conceptually simple but computationally inefficient. We choose the value of n to be 6, so the recursive calculations stay simple and manageable. Using a small value makes it easier to follow how the recursive Fibonacci function works. It also helps us clearly see the repeated subproblems that appear during the computation. This focused example lets us observe the function's behavior without getting lost in large numbers. We compute a Fibonacci number for a chosen value of n using a naive recursive function, and we wrap this function with a decorator that counts how many times each input value is recalculated. The final Fibonacci value is stored in a result variable, but the main purpose of this setup is to track how often each subproblem is solved. By examining these counts, we can clearly see the inefficiency of naive recursion and how it repeatedly recomputes the same subproblems. This makes the idea of overlapping subproblems in recursion more concrete and easier to understand. We display the output of the Fibonacci function for the chosen input value of n. For n equal to 6, the program prints the final Fibonacci number it computes. This output lets us confirm that the recursive implementation is working correctly for that input. We begin by printing a short message to explain that we are about to show how many times each Fibonacci subproblem is recomputed. This prepares the listener to focus on the counts for each input value. By examining these repeated calculations, we can clearly see the inefficiency of the naive recursive approach to computing Fibonacci numbers. We look through the dictionary that records how many times each Fibonacci subproblem is called, using its keys as the different input values to the Fibonacci function. By sorting these keys, we list the subproblems in a clear, ordered way. This makes it easy to see how often each specific Fibonacci value is recomputed and helps us visualize the inefficiency of the naive recursive approach, where the same subproblems are solved over and over again. This code reports each input value given to the Fibonacci function and how many times that value is used in the recursion. By counting how often each input appears, it reveals that the same subproblems are solved repeatedly. This makes the idea of repeated subproblems in recursive algorithms concrete and easier to understand. Overall, it highlights the inefficiency that can arise when recursion recomputes the same values many times. This script uses a simple recursive method to compute Fibonacci numbers and demonstrates the idea of overlapping subproblems. A decorator tracks how many times each Fibonacci value is recalculated while computing the sixth Fibonacci number, which equals 8. The output shows that smaller Fibonacci numbers are computed many times, revealing the inefficiency of the naive recursive approach. This makes it clear why dynamic programming, which stores intermediate results, is more efficient for problems like this. Yielding optimal solutions. Dynamic programming is a method for solving large problems by combining solutions to smaller subproblems, a property known as optimal substructure. Once you determine the best way to solve each smaller part, the overall optimal solution is just the combination of those best parts. You do not need to recompute or reconsider each segment in a larger plan, because its optimal solution remains valid. Using this idea, dynamic programming builds up the final answer, either from the bottom up or by refining it from the top down. To build optimal solutions, you first break the main problem into smaller, manageable subproblems by defining a state that contains all the information needed at each step. You then determine how to construct the overall solution from these states, such as using the remaining budget and available options in an investment planning problem. At each state, you choose the best action by comparing the outcomes of its smaller, related states, ensuring that each decision is based on previously computed optimal results. This systematic process lets you find the best overall plan without having to try every possible combination. Dynamic programming works best when a problem has optimal substructure, meaning that solving each smaller part in the best possible way leads to the best overall solution. If a locally optimal choice for a small part can harm the global result, as can happen in complex scheduling with many rules, then dynamic programming is not appropriate. But when subproblems are independent, as in many routing or resource allocation tasks, you can solve each one separately and then combine their solutions with confidence. The key is to define subproblems whose solutions can be reused without creating conflicts in the final answer. Python code, building optimal solutions. This section explains how dynamic programming builds an optimal solution by combining smaller optimal parts. It shows how the cost of each segment of a route is computed once and then reused when calculating the total cost of the full trip. To make this clear, it contrasts a naive, recursive approach, which repeatedly recomputes the same segment costs, with a memoized dynamic programming approach, which stores and reuses those results. Any unrelated setup commands, such as installing libraries, are not part of the core explanation. We define a dictionary called segments that links each pair of cities to the distance between them in miles. For instance, it stores that the distance from city A to city B is 100 miles, from B to C is 150 miles, and directly from A to C is 260 miles. This structure lets us quickly look up the distance between any two connected cities. Having these distances organized in one place will be essential for calculating travel costs later on. We set a fixed fuel cost of 25 cents per mile and use this value to calculate the cost of traveling between cities based on distance. Defining it as a separate value keeps all cost calculations consistent throughout the program. It also makes it easy to update the fuel price later without changing the rest of the code. We use a simple recursive function to find the minimal travel cost between two cities. It first checks whether there is a direct route between the start and end cities. If there is, it returns the distance multiplied by the fuel price per mile. If the route goes from city A to city C through city B, it recursively computes the cost from A to B and from B to C, then adds these values. If neither a direct route nor the specific route through B exists. The function returns infinity to indicate that no valid path is available. We begin by creating an empty dictionary called memo, which will store solutions to smaller subproblems that we have already solved. By saving these results, we avoid doing the same calculations again, which saves time and computing power. This approach is called memoization and is a central idea in dynamic programming. It lets us efficiently solve complex problems by reusing previously computed optimal solutions instead of recomputing them from scratch. We use a dynamic programming function to find the minimum travel cost between two cities. It builds a unique key from the start and end cities and first checks a memo dictionary to reuse any previously computed result. If the segment is directly available, it multiplies the distance by the fuel price per mile, stores that cost in the memo, and returns it. For trips that go through an intermediate city, such as from A to C via B, it adds the costs of each smaller segment using the same function recursively and stores the total. If no valid combination of segments exists, it records the cost as infinity to indicate that the trip is not possible and returns that value. We begin by computing the minimal cost of a road trip from city A to city C using a simple recursive method. This naive approach explores both direct and indirect routes between the two cities to find the cheapest option. The final result of this straightforward but potentially inefficient calculation is stored as the total minimal cost for traveling from A to C. To find the minimal cost of traveling from city A to city C, we use dynamic programming. We call a function that computes this minimal cost while using memoization to store results of smaller subproblems. By reusing these stored results, instead of recalculating them, we avoid redundant work. This approach lets us determine the trip cost efficiently and ensures good performance. We now show the result of using the naive method to find the minimal travel cost from city A to city C. The final cost is rounded to 2 decimal places to keep it easy to read. This example illustrates how the naive approach builds the total trip cost by adding together the best costs for each individual segment of the journey. We use dynamic programming to find the minimal cost of traveling from city A to city C, then round the final value to 2 decimal places for clarity. We compare this result with the cost obtained from a straightforward, naive calculation. When both methods give the same total cost, it confirms that the dynamic programming approach is correct and effectively optimizes the solution. This script illustrates dynamic programming by comparing a naive recursive method with a memoized approach to finding the minimal cost of a road trip. It models segments between cities with given distances and uses a fixed fuel price to compute travel cost. The naive recursion repeatedly recalculates the same subproblems, while the dynamic programming version stores and reuses intermediate results. Both methods produce the same minimal cost from city A to city C. But the memoized dynamic programming solution is significantly more efficient, demonstrating the benefit of building the final answer from optimal subparts. Recursion to dynamic programming. When facing a complex problem, it often helps to begin with a simple recursive solution that breaks the task into smaller subproblems. This reveals the structure of the problem, including the smallest case you can solve directly and how larger cases reduce to smaller ones. However, recursion can end up solving the same subproblems many times, such as repeatedly counting the ways to climb stairs with 1 or 2 steps. When you notice this kind of repetition, it is a sign that dynamic programming can improve efficiency by storing and reusing the results of those subproblems instead of recomputing them. To move from recursion to dynamic programming, view the recursion tree as a set of overlapping subproblems instead of separate calls. Identify each unique subproblem, solve it once, store its result, and reuse that result whenever the same subproblem appears again. You can think of this as labeling subproblems, such as by remaining capacity, and organizing their solutions in a conceptual table. The recursive structure still defines which results depend on which, but the actual computation now flows through this table, eliminating redundant work while keeping the logic clear. Dynamic programming is useful when a problem can be described recursively and the same intermediate situations keep appearing. In real-world tasks like planning a road trip with fuel limits or scheduling with deadlines, the best current choice often depends on future options, and different decision paths can lead to the same state. When you see these overlapping subproblems, you can switch to dynamic programming by storing the solutions to each unique state. This lets you solve each state once and reuse the results, turning a purely recursive idea into a more scalable and efficient method. Python code, recursion to dynamic programming. We want to show how a simple recursive solution for the stair climbing problem can be transformed into dynamic programming using memoization. First, we use a naive recursive approach and observe that it makes many repeated calls for the same subproblems. Then we introduce memoization, where we store and reuse results of previous calls instead of recomputing them. By counting how many times the function is called in both versions, we can clearly see that the memoized dynamic programming solution performs far less repeated work than the naive recursion. The line with the install command is just a placeholder showing where you might install a library if it were needed. In this particular script, it is not required and is included only as an example. Educational scripts often use this kind of line to indicate where dependencies would be managed. Here, it simply serves as a reminder or template for possible future use. We import the functools library so we can use its memoization feature, which stores results of function calls that have already been computed. This is especially useful for recursive functions, where the same inputs may occur many times. By reusing stored results instead of recalculating them, we avoid redundant work. This idea is central to dynamic programming and greatly improves the efficiency of our algorithms. We use a simple recursive function to count how many ways we can climb a staircase. The function takes the number of steps left and a counter that tracks how many times the function is called, and it increases this counter on every call. If there are no steps remaining, we have found a valid way to climb the stairs and return 1. If the steps remaining are negative, the path is invalid and we return 0. Otherwise, the function returns the sum of 2 recursive calls that represent taking either one step or two steps from the current position. We use dynamic programming with memoization to compute how many ways there are to climb a staircase. A decorator from the standard library caches previous results, so the function does not repeat the same calculations. If there are 0 steps left, the function returns 1, meaning there is exactly one valid way to finish. If the remaining steps are negative, it returns 0, meaning there is no valid way. For all other cases, it recursively adds the number of ways to climb by taking one step and by taking two steps, reusing cached values whenever possible to improve efficiency. We set the total number of stairs to 10 to define the size of the problem we are solving. This value represents a small staircase and serves as the input to our functions that compute how many different ways there are to climb it. By choosing and adjusting this number, we can easily change the problem size and compare how the recursive and dynamic programming approaches perform for different inputs. We create a list called the naive counter with a single element set to 0 to track how many times the naive recursive function is called. This list acts as a mutable container that can be updated inside the recursive function. Because integers in Python cannot be changed in place, using a list lets us modify the count directly. As the function calls itself, it updates this shared list element, giving us a running total of all recursive calls. We begin by using a naive recursive function to compute the number of ways to climb 10 stairs. This function takes the total number of stairs and a counter that starts at 0. The counter records how many times the recursive function is called. By examining this count, we can see how many recursive calls are needed and understand how inefficient the naive approach is for this problem. We solve the stair climbing problem using dynamic programming with memoization. A function computes how many ways there are to climb the stairs and stores each result once it is calculated. When the same subproblem appears again, the function reuses the stored value instead of recomputing it. By calling this function with the total number of stairs, we efficiently find the answer by leveraging these cached results from overlapping subproblems. To find how many distinct subproblems were solved in a dynamic programming approach, we look at the cache statistics of the function. We add the number of cache hits, which count how often a stored result was reused, to the number of cache misses, which count how often a new result had to be computed. This total equals the number of unique subproblems that were actually solved. It also shows how much efficiency was gained by avoiding repeated calculations. We compare the results of climbing the stairs using two methods. We first state the total number of stairs, then give the number of ways found by the naive recursive method, and then the number of ways found by the dynamic programming method. Both methods produce the same count of ways to climb the stairs, but the dynamic programming approach does so with far fewer function calls, making it much more efficient. We print the total number of recursive calls made by the naive approach to show how large the full recursion tree becomes without memoization. This number tells us how many times the function actually runs when no optimization is used. By looking at this count, we can clearly see how inefficient the naive method is. We print the total number of calls made by the dynamic programming approach to show how many distinct subproblems were actually solved. This number is lower because memoization stores the results of subproblems that have already been computed. By reusing these stored results, dynamic programming avoids repeating the same calculations. This demonstrates why dynamic programming is more efficient than naive recursion. This script compares a naive recursive solution and a dynamic programming solution with memoization for the classic stair-climbing problem, where you count how many ways you can climb 10 steps by taking 1 or 2 steps at a time. The naive recursive version explores all possible combinations and repeats many calculations, which shows up as a very large number of function calls. The dynamic programming version uses a cache to store results of subproblems it has already solved. So it avoids redundant work and makes far fewer calls. Both methods produce the same final count of ways to climb the stairs, but the memoized approach is much more efficient, illustrating the power of caching in recursive algorithms. Designing recurrences. Subproblem state design. In dynamic programming, the crucial step is designing the subproblem state, which means deciding what each subproblem represents. You do this by describing your current position in the problem using a small set of parameters. These parameters must contain all the information needed to make optimal choices for the remaining part of the problem, without revisiting the full input or past decisions. For example, a state might track your current city and which cities you have visited, or the current day and remaining hours. The goal is to choose this snapshot so that the recurrence relation becomes simple, efficient, and correct. To design a subproblem state, imagine pausing halfway through a task and asking what minimal information you would need to finish it optimally. That essential information is your state. In text editing, this could be the current positions in both documents, in financial planning, the current year and accumulated capital, and in logistics, the current warehouse and remaining goods. A good state contains everything needed to complete the task from that point onward, without relying on any details about how you reached that state. When designing states for dynamic programming, you must balance completeness with efficiency. If the state leaves out important information, the solution can ignore key constraints. But if it includes too much detail, the number of states becomes unmanageable. The aim is to capture only what truly affects future decisions, such as positions, remaining resources, or a compact summary of past actions. By carefully refining the state definition and removing unnecessary details, you get a model that is both accurate and computationally practical. Formulating recurrence relations. Once you have a clear subproblem state, the next step is to define a recurrence relation, which explains how to build the solution to a larger subproblem from solutions to smaller ones. To do this, you identify the key decision or event that connects the current state to earlier states. In a planning problem, this might mean deciding how adding or skipping a task today relates to schedules you have already solved for previous days. In a pathfinding problem, it could mean finding the best route to an intersection by extending the best route from a neighboring intersection. In all cases, the goal is to capture this logic so a computer can systematically combine smaller solutions into a solution for the current state. To design a recurrence, you focus on a key decision at each step and express the value of the current state in terms of the best outcomes of those choices. Whether it is choosing the next city on a road trip or selecting an investment in a given month, the recurrence links the current decision to the optimal result from the remaining steps. This approach does not solve the whole problem at once. Instead, It breaks it into smaller stages whose solutions can be reused. The crucial part is making sure each term in the recurrence corresponds exactly to a clearly defined subproblem state. When building recurrence relations in dynamic programming, you must carefully distinguish between different types of choices and transitions. For instance, you need to separate allowed from forbidden options, or cheap from expensive moves, because each leads to a different subproblem. In applications like resource allocation or scheduling, this means treating feasible and infeasible options, or overlapping and non-overlapping tasks, in different ways. By encoding these distinctions directly into your recurrence, the algorithm respects all constraints while still reusing subproblem solutions efficiently. With practice, you will learn to express complex decision processes as clear, structured recurrences. Validating base cases. When you design a dynamic programming solution, you must carefully validate the base cases that support your recurrence. These base cases are the simplest situations where the answer is known directly, such as when there are no tasks or no days. Clearly define what each state means, then decide what the correct result should be in these minimal scenarios. Doing this ensures the base cases match the problem's meaning, prevents infinite recursion or wrong answers, and gives your solution a solid and reliable foundation. When testing base cases, use small, concrete examples to check that your definitions match common sense. For a minimum travel cost problem, think about what should happen with 0 flights, or when the start and end cities are the same. With no flights, reaching a different city should be impossible or extremely expensive, while staying in the same city should cost nothing. Confirming these intuitive outcomes helps you catch inconsistencies early, much like testing edge cases in software, to ensure the system behaves logically at its limits. When designing a dynamic programming solution, make sure your base cases fit smoothly with the recurrence and cover every way the process can start. Every chain of recursive calls must eventually reach a base case that returns a clear answer. So mentally trace the recursion to confirm this. In a financial planning example, this means defining base cases for the earliest year and for situations with no income or investments. Then checking that the recurrence naturally leads into these situations. Look carefully for off-by-one errors, missing scenarios, or contradictions between the base cases and the recurrence. Well-chosen base cases create a reliable foundation for the entire solution. Python code. Validating base cases. In this segment, we focus on how to validate base cases in a very small dynamic programming example. We use a simple climbing stairs problem to compare correct and incorrect base case choices. By examining how each set of base cases behaves on the smallest input values, we can see that wrong base cases may still run without errors, but quietly produce wrong answers. This highlights why carefully checking base cases on tiny examples is essential for getting dynamic programming solutions right. The line with the pip install command is just a placeholder comment that indicates no extra packages are required for this script. It tells you the code runs using only standard Python libraries. This means you do not need to install anything additional. As a result, the script stays simple, easy to run, and free from extra dependencies or setup steps. We define a recursive function and use memoization to avoid repeating the same calculations. To do this, we apply a cache decorator from the standard library, which automatically stores the results of previous function calls. When the function is called again with the same inputs, it returns the saved result instead of computing it again. This approach is especially useful in dynamic programming problems with overlapping subproblems, such as counting the number of ways to climb a set of stairs. We define a function to count how many ways you can climb a staircase when you are allowed to take either one step or two steps at a time. To make this efficient, we use a memoization decorator from the standard library so that repeated calculations are cached and reused. The function returns one way when the number of remaining steps is 0, meaning you have exactly reached the top. It returns 0 ways when the number of steps is negative, meaning you have overshot and the path is invalid. In all other cases, it uses recursion to add together the number of ways to finish when taking one step and when taking two steps. This example defines a memoized recursive function called ways wrong to illustrate how incorrect base cases can break a dynamic programming solution. It wrongly returns 0 when the number of steps is 0, implying there are no ways to stay at the bottom. And it returns 1 for negative step counts, treating overshooting as a valid path. The function otherwise uses the same recurrence as the correct version, combining results from 1 step smaller and 2 steps smaller. This setup shows that even if the recursive relation is right, bad base cases can still produce misleading results. A compare small values function prints a side-by-side comparison of results from two different stair climbing functions. It begins with a header that labels the columns as the number of steps, the correct number of ways to climb, and the wrong number of ways. It then loops from 0 up to a chosen maximum number of steps. And for each value, it prints the step count along with the outputs of the correct and incorrect functions. This lets us quickly see how the two functions differ for small step counts and reveals the effect of using correct versus incorrect base cases. The code runs a comparison between two different implementations for counting how many ways you can climb a set of stairs. It uses a helper function to print the results for small numbers of steps, from 0 to 5. By looking at how each version behaves on these small inputs, we can check whether the recursive base cases are correct. This highlights how different choices for the base cases directly affect the function's output. This script shows why correctly defining base cases is crucial in dynamic programming. Using the example of counting ways to climb stairs with 1 or 2 steps at a time, one version of the function is correct because it treats 0 steps as having one valid way and negative steps as having no valid ways, which leads to logical results. The other version is incorrect because it does the opposite, assigning 0 ways to 0 steps and 1 way to negative steps, which produces flawed outcomes. Comparing their outputs for small numbers of steps up to 5 reveals that the correct function behaves as expected, while the incorrect one quietly produces wrong answers, illustrating how small base case mistakes can undermine recursive algorithms. Python memoization basics. Dictionary-based memoization. Dictionary-based memoization speeds up recursive functions by saving the results of expensive calls and reusing them instead of recomputing. In Python, this is done with a dictionary that maps each input to its corresponding output. It is especially useful for problems with repeated subproblems, such as sequences or game states. By avoiding repeated work, memoization can transform an algorithm that would otherwise take exponential time into one that runs in polynomial time, while still keeping the code in a clear, recursive style. When you use a dictionary for memoization in a recursive function, you first check whether the answer for the current input has already been stored. If it has, you immediately return that stored value and skip any further recursive work. If it has not, the function runs its usual recursive steps to solve the subproblems and combine their results. Before returning this new result, it saves it in the dictionary. As more results are stored and reused, the function becomes faster because it avoids repeating the same deep recursive calls. Dictionary-based memoization is a flexible technique that speeds up recursive algorithms by storing and reusing previously computed results. It is useful in real-world tasks, such as route planning, where it avoids recalculating similar travel costs, and in financial models, where it reuses values for repeated market states. It also supports natural language processing by caching intermediate parsing results. In this way, memoization preserves the clarity of recursion while achieving performance comparable to dynamic programming. Python code. Dictionary-based memoization. This lesson uses the Fibonacci sequence to demonstrate dictionary-based memoization. We first compare a naive recursive solution, which repeatedly recomputes the same values, with a memoized recursive version that stores results in a dictionary. Each time the memoized function computes a Fibonacci number, it saves the result in the dictionary and checks this dictionary before doing any new work. By reusing previously computed subproblem results, the memoized approach runs much faster, even for relatively small input values. This comment simply notes that if extra libraries were ever needed, they could be installed with a package manager. But for this particular script, the built-in Python standard library is enough. It serves as a reminder that developers should think about and document any external dependencies when they write or share code. In this case, no additional installation steps are required. We begin by importing the time module from Python's standard library, so we can work with time-related functions. In this context, we use it to measure how long different parts of our code take to run. By recording the time just before and just after a specific operation, we can calculate its execution time. This lets us compare the performance of different solutions to the same problem and see which one is faster. We define a Fibonacci function using a simple recursive method. It takes an integer input and immediately returns the same value when the input is 0 or 1, since these are the base cases of the sequence. For any larger input, the function calls itself with the previous two integers and returns the sum of those results. This mirrors the mathematical definition of Fibonacci numbers, but it becomes inefficient for large inputs because many values are recalculated multiple times. To use memoization for the Fibonacci sequence, we create an empty dictionary called a cache to store results of Fibonacci values that have already been computed. Each time the recursive function runs, it first checks this cache to see if the answer is already available. If it is, the function returns the stored value instead of recalculating it. This reuse of previous results avoids redundant work and greatly improves the efficiency of the recursive Fibonacci computation, especially for larger input values. The memoized Fibonacci function takes an integer and first checks a cache dictionary to see if the result was already computed. If the value is in the cache, it returns it immediately, avoiding repeated work. If the number is not cached and is 0 or 1, it stores that base case in the cache and returns it. For larger numbers, it recursively computes the Fibonacci value as the sum of the results for the previous two numbers, stores this result in the cache, and then returns it. This use of caching makes repeated Fibonacci calculations much more efficient. We choose the value 30 for n because it is a Fibonacci position where the performance gap between a naive recursive solution and a memoized solution becomes clear. At this size, the naive approach starts to slow down noticeably, while the memoized version remains efficient. Using this value helps us clearly demonstrate the practical benefits of memoization in improving performance. We first record the current time using the time module to mark when the naive Fibonacci calculation begins. Then we run the basic, unoptimized Fibonacci function for the chosen position n. After the function finishes, we record the current time again to mark the end of the computation. By comparing the start and end times, we can determine how long the naive Fibonacci approach takes to run. We measure the performance of the memoized Fibonacci function by recording the time before and after it runs. The function computes a Fibonacci number at a chosen index while storing previously calculated values in a dictionary to avoid repeating work. By comparing the total execution time of this memoized version with the time taken by the naive recursive method, we can see how much efficiency is gained through memoization. The code first prints the result of the naive Fibonacci calculation, along with how long it took to run, with the time rounded for easier reading. It then does the same for the memoized Fibonacci version, showing its result and the rounded computation time. Finally, it prints how many entries are stored in the cache, indicating how many Fibonacci values were saved and reused during the memoized computation. This script compares a naive recursive method for computing Fibonacci numbers with a memoized method that uses a cache. The naive version repeatedly recalculates the same values, so it takes much longer to find the 30th Fibonacci number. In contrast, the memoized version stores each result in a dictionary and quickly reuses these stored values, leading to much faster execution. After both methods run, the script prints the Fibonacci result, the time each method took, and how many unique Fibonacci numbers were stored in the cache during the memoized run. LRU cache decorator. In Python, you can add memoization to a recursive function by using the built-in least recently used cache decorator, which wraps the function and remembers recent results based on the input arguments. When the function is called again with the same arguments, it returns the stored result immediately, greatly reducing the time needed and often turning an exponential process into something closer to linear time. This approach keeps the caching separate from the main logic of the function, so you can focus on writing a clear recursive definition, while the decorator automatically handles optimization. It is an accessible way for learners to benefit from memoization without managing their own cache structures. The cache decorator uses a least recently used strategy, meaning it stores only a limited number of recent argument combinations and removes the one used longest ago when it needs space. This works well when recent computations are more likely to be needed again, such as in simulations or financial processing. By adjusting the cache size, you can trade off memory usage against performance, which is especially important for long-running programs or those with many possible input values. Using a least recently used cache decorator in Python helps you write clean, predictable functions that always return the same result for the same inputs without relying on global state. This style fits naturally with dynamic programming, where you solve a problem by breaking it into smaller subproblems defined by specific parameters. By applying the decorator to recursive functions that compute things like travel costs, language model probabilities, or game scores, you can speed up your code while keeping your focus on the problem itself instead of on managing the cache. Python code LRU cache decorator. This lesson shows how to use the LRU cache decorator from the functools module to add simple memoization to a recursive function. We compare a naive recursive implementation of the Fibonacci sequence with a version that uses LRU cache to store and reuse previously computed values. By running both versions on small Fibonacci indices, we can see that they produce identical results, but the cached version runs noticeably faster. This demonstrates how LRU cache can improve performance in recursive algorithms without changing their logic. You do not need to run any pip install commands for the functools module because it is included in Python's standard library. This means functools comes built into any normal Python installation. As a result, it is available for you to use right away without any separate installation steps. We begin by importing the time module so we can measure how long different parts of our program take to run. This timing information lets us compare the performance of different implementations. By knowing which version of our code runs faster, we can make more informed decisions about optimization and efficiency. We use the least recently used cache decorator from Python's functionals module to add caching to a function. Caching means the function remembers the results of previous calls and reuses them when it is called again with the same inputs. This reduces the need to recompute expensive operations and can greatly speed up programs. It is especially helpful for functions that are called many times with repeated arguments, such as recursive implementations of the Fibonacci sequence. We use a simple function called fibnaive to compute Fibonacci numbers without any caching. It takes a position n in the sequence and first checks if n is 0 or 1. In those cases, it just returns n, since the first two Fibonacci numbers are 0 and 1. For larger n, it uses recursion by calling itself with n-1 and n-2 and adding those results. This directly follows the mathematical rule that each Fibonacci number is the sum of the two previous numbers. We use a least recently used cached decorator with a maximum size of 128 to automatically store and reuse function results, which speeds up repeated calculations. With this in place, we define a Fibonacci function that follows the usual mathematical definition. For the base cases, when the input is 0 or 1, the function simply returns that value. For all other inputs, it calls itself with the two previous numbers and returns their sum. This recursive approach becomes efficient because the decorator caches previously computed Fibonacci values and avoids redundant work. We choose the Fibonacci index to be 32 so it is large enough to highlight performance differences. This index lets us clearly compare how long it takes to compute the same value using a naive recursive method versus an optimized method that uses caching. By timing both approaches on this larger index, the impact of optimization becomes much more obvious. We begin by recording the current time using the performance counter from the time module, which is a high-resolution timer suitable for measuring short durations accurately. This timestamp marks the start of the naive Fibonacci computation. After the computation finishes, we compare the end time with this start time to determine how long the calculation took. This code computes the Fibonacci number at position n using a simple recursive function that does not store any previous results. Each time it needs a Fibonacci value, it recalculates it from scratch, even if that value was already computed earlier. This makes the method easy to understand, but very inefficient for larger n, because the same calculations are repeated many times. We measure how long the naive Fibonacci computation takes by using the time module's performance counter. First, we record the start time. Then we record the current time after the computation finishes. Subtracting the start time from the later time gives us the elapsed time. This tells us how long the naive approach took, so we can compare its performance with the cached version. We begin by recording the current time using the performance counter from the time module to establish a starting point. This timestamp marks when the cached Fibonacci computation starts. After the computation finishes, we compare the new time to this starting point to find the total time taken. This lets us measure how long the cached version runs and compare its execution time with the naive implementation. We are computing the Fibonacci number at position n using a version of the Fibonacci function that has been optimized with a least recently used cache. This cache, provided by the functools library, stores results of previous calls, so the function does not recompute values it has already found. When we call the cached Fibonacci function with n, it can quickly return the answer by reusing stored results. This makes the computation much faster and more efficient than the basic recursive approach that recalculates the same values many times. To measure how long the cached Fibonacci computation takes, we record the start time, then later subtract it from the current time using a high-precision performance counter from the time module. This difference gives the elapsed time for the cached version. We can then compare this elapsed time with the time taken by the naive Fibonacci approach to evaluate which method is more efficient. The program prints the Fibonacci position being calculated and shows the results from both the naive method and the cached method. By displaying these side by side, it lets you directly compare the two outputs. This confirms that both approaches produce the same Fibonacci number for the given position. We measure how long it takes to compute the naive Fibonacci sequence and then print that elapsed time. The result is rounded to 6 decimal places and formatted as a readable string in seconds. This precise timing helps us evaluate the performance of the naive approach by showing exactly how long the computation required. We measure how long it takes to compute a Fibonacci number using the cached version of the algorithm and report the elapsed time, rounded to 6 decimal places. This timing shows how quickly the cached method runs. By comparing it to the time from the naive method, we can clearly see the efficiency gained from using caching. The code measures how much faster the cached Fibonacci computation is compared to the naive version by dividing the naive running time by the cached running time. This calculation produces a speedup factor that shows how many times faster the cached approach runs. The value is rounded to 2 decimal places for readability, then printed to clearly show the performance improvement gained from using caching. This script compares 2 ways of computing the Fibonacci number at index 32, a simple recursive method and an optimized method that uses caching. The naive recursive version repeatedly recalculates the same values, which makes it much slower. The cached version stores previously computed results and reuses them, greatly reducing the total computation time. Both methods produce the same Fibonacci number, but the script shows that the cached approach runs much faster by reporting each method's execution time and a speedup factor that indicates how many times quicker the cached version is. Measuring speedups empirically. To see the real benefit of memoization, directly compare it with a naive recursive solution by measuring how long each one takes. Use the same computationally intensive task, such as computing a recursive sequence, and run both methods under identical conditions. Test them across different input sizes and record the time for each run. By observing how the running time grows as the input increases, you can clearly see the speed advantage of memoization over the naive approach. When running timing experiments, use a systematic approach so your results are reliable. Run each version several times on the same input size and use the average or the minimum time to reduce the impact of random background activity. Make sure both implementations do exactly the same work and differ only in whether they use memoization. For example, if you compare naive and memoized versions of a recursive staircase counting function, they must take the same inputs and produce the same outputs, with caching as the only change. This consistency lets you clearly see how much memoization affects performance. When you compare timing results, small inputs may show similar performance for both the naive and memoized versions, and memoization can even appear slightly slower because of cache overhead. As input sizes grow, however, the naive approach often becomes too slow to be practical, while memoization stays efficient by reusing previous computations. This pattern mirrors real-world tasks like financial modeling or AI, where larger problems demand smarter computation. By plotting and studying these results, you can clearly see where memoization becomes beneficial and turn theoretical ideas into practical understanding. Python code, measuring speedups empirically. Measure the performance benefits of memoization by running simple timing experiments. Compare how long it takes to compute Fibonacci numbers using a naive recursive version versus a memoized version as the input size increases. Record and print the timing results so you can clearly see and quantify the empirical speedups provided by memoization. The comment is explaining that you do not need to run any pip install commands because the code only uses the Python standard library. All the required features are already built into Python, so no extra packages are necessary. This makes setup easier and ensures the code will run in any normal Python installation without additional dependencies. We begin by importing the time module so we can measure how long our code takes to run. This module lets us track the elapsed time for different parts of a program. By doing this, we can compare how efficient various implementations are. In short, timing our code is essential for performance analysis and optimization. This function computes the Fibonacci number for a given input using a simple recursive strategy. It first checks whether the input is 0 or 1, and in those cases, returns the input itself. For larger values, it calls itself twice to get the results for 1 less and 2 less than the input, then adds those results together. This mirrors the mathematical definition of the Fibonacci sequence, but does not use optimizations like memoization, so it repeats many calculations and becomes inefficient for large inputs. To create a memoized Fibonacci function, we first set up an empty dictionary called a memo cache. This cache stores Fibonacci values that have already been computed. When we need a Fibonacci number, we first check the cache and reuse the stored result if it exists. By avoiding repeated calculations, this approach greatly speeds up the computation for larger input values. The memoized Fibonacci function computes Fibonacci numbers efficiently by storing previously calculated results in a cache. When asked for a value, it first checks if the result is already in the cache and returns it immediately if found. If the input is 0 or 1 and not yet cached, it stores that value directly, since the Fibonacci number equals the input in these cases. For larger inputs, it recursively computes the 2 preceding Fibonacci numbers, adds them, saves the sum in the cache, and then returns it. This approach ensures each Fibonacci number is calculated only once, greatly reducing redundant work. This helper function measures how long another function takes to run with a given input. It first records a precise start time using a performance counter, then calls the target function with the provided argument and saves its result. After the call finishes, it records the end time and computes the difference between the 2 timestamps. Finally, it returns both the function's result and the measured time, making it easy to time any function by passing it and its input to this tool. We choose input sizes of 20, 25, 30, and 32 to compare the naive and memoized Fibonacci implementations. These values are large enough that the difference in execution time between the 2 approaches becomes clear. Using these sizes ensures that the timing gap is significant and easy to observe in practice. We begin by printing a header for the results table that will compare 2 Fibonacci implementations. The first column shows the input size. The second shows the time in seconds for the naive recursive version. and the third shows the time for the memoized version. The final column indicates whether both methods produce the same Fibonacci number. This structure lets us clearly see both performance differences and correctness at a glance. We test performance by looping over different input sizes and, for each one, timing how long the naive Fibonacci function takes to compute the result. We repeat this process with the memoized Fibonacci function, recording both its result and its execution time. We then compare the outputs from the two implementations to confirm they produce the same Fibonacci number. Finally, we neatly display the input size, the time for the naive version, the time for the memoized version, and whether their results match, so it is easy to compare their performance. This script compares two ways of computing Fibonacci numbers: a simple recursive method and a memoized method that uses a cache. It measures how long each approach takes for several input sizes and shows that the naive recursive version becomes very slow as the input grows, because it repeats the same calculations many times. In contrast, the memoized version stores previously computed values, greatly reducing the work needed and running much faster. The output reports the input size, the time for each method, and verifies that both produce the same Fibonacci result, highlighting the significant speedup gained from memoization for larger inputs. In this lecture, you learned to identify overlapping subproblems and optimal substructure in candidate problems, derive recurrence relations that define dynamic programming solutions, and implement memoized recursive solutions in Python to improve performance over naive recursion. In the next lecture, Lecture B, we will go over tabulation patterns.
Thank you for your attention. See you all in the next lecture.